So I'm going to give a little bit of an introduction to the session, and then we'll jump into the presentation. So just to give a very quick primer on what are virtual stores, so you know that you're in the right room, or if you're not familiar with virtual stores, just to make sure that you start to get familiar with them. So this is my very simplistic view of what virtual stores are, which is basically the first thing that the user is going to do is that they're going to read the references to chunk locations and netcdf files, and then instead of downloading those entire netcdf files, they can access just the chunks that they want. So my tagline for this is virtual stores unlock cloud-friendly access to archival files via partial access. Let me see if I can minimize this for folks in the room. Okay. My name is Amy. Thank you for being here. I am the chair of the Cloud Computing Cluster, and I currently facilitate a virtual stores co-working session. So if this is something you want to continue talking about and getting involved in, please let me know so that I can add you to that group. So the goals for this session are for everybody here to be able to explain what problems virtual stores solve and why, describe one or more use cases, and be aware of important metadata considerations and access tooling. So the agenda is going to be the welcome, which is what we're doing right now. And then we're going to hear first from Tom Nicholas at Earthmover, who is going to give a sort of plenary style presentation for this session that's called Virtual Stores from Theory to Production. Then I want to get everybody talking. So we're going to have a group discussion. So I'm going to sort of break folks into groups amongst the room, and we're going to have a discussion question. Those discussion questions are already in the notes document. So if you want to take a second to open up the notes document, if you want to take a look at those questions ahead of time, also to prepare in case you want to be someone who contributes to taking notes during the discussion, that would be very helpful. And then we're going to, after the group discussion, hear from Hailiang and Eli about use cases at NASA JESDISC and NOAA. And then we're going to go into another group discussion. And then we're going to have a series of shorter talks for Max on metadata, Luis on accessibility, and then James and Miguel on chunk manifest as a protocol. And then we're going to have a wrap up and preview for part 2, which will be the session at 4 p.m., which will be a working session. I'll talk more about that in a little bit here. Okay, so some housekeeping. So we invite you to be present. So I invite you to take this opportunity to really be present and pay attention to the presentations as well as participate in the conversation. As you know, I'm not going to go around wagging my finger at you, but it's a nice opportunity to be here in person and really participate and listen. Questions. So each speaker, I will try to allow one question after each presentation for speakers. There will be additional time at the end of the session, and of course the break as well for additional questions, and part 2 in the working session. So we won't have a lot of time for questions, but I just wanted to mention that there will be other opportunities as well. If you are online as well, you are welcome to post questions in the chat, and Max can help moderate those questions. As well, please adhere to the community participation guidelines, specifically during the discussion. So to be respectful, direct but professional, inclusive, understand different perspectives, appreciate and accommodate our similarities and differences, and lead by example. So like I said, there's going to be 2 group discussions in small groups. So there's going to be questions in the notes document, like I said, in the bottom. If you scroll down, there's also a link to them as headers. So in the small groups of 4 to 6, we're going to have a note taker and a facilitator who will, take notes from people's responses to those questions. And I think that those notes and those reflections will really be informative to us that are designing and thinking about virtual stores moving forward, and inform how we move forward with this technology. And then there's the QR code to the notes document here if you don't have it easily accessible. So I'll leave that up for a second in case anybody wants to open that up. It's also accessible at this short link, bit.ly ESIP /2026-virtual. Okay, I hope I didn't take up too much time. So I'm ready to hand it off to Tom for our first presentation.
All right. Yes, so I'm going to talk to you for a little while about everything to do with virtual stores. It's like a broad, high-level overview that hopefully will like ground the rest of the talks and give you some context. Just quickly to introduce myself more thoroughly, I'm Tom Nicholas. I'm a software engineer. I was originally a plasma physicist by training, and then I pivoted to geoscience data. So I used to work with simulation data of hot swirling things, and then I worked with simulation data of cold swirling things. But the common link was always like data and software problems. And I ended up becoming an open source maintainer, particularly of Xarray. I made Xarray data tree, some of you mentioned yesterday. And I made this project called Virtualizar that I'm going to talk about a little bit. And I now work at this company called Earthmover, who made IceChunk. So I help out with the maintenance of that. We also have Joe over there, who is from Earthmover as well, here at ESIP. And Earthmove is a public benefit corporation. This is our mission statement, and you'll hear a bit more about like technology in the rest of the talk. So to give you an outline of what I want to talk about, first we've got to do a couple of definitions just so we know what we're actually even talking about, what we mean by the word virtual in this context. Then I want to motivate why this idea is helpful at all. And it turns out there's like actually a number of different reasons that are like orthogonal reasons why this is helpful. Then briefly, like how would a practitioner go about making such a virtual store? Do a whistle-stop tour of various examples of people using virtual stores in the wild today and things that people have successfully done with them. If I haven't run out of time at that point, I'll give a little history of where this even came from and the problems, the sort of history of problems that were solved as this technology built up, and then extrapolate that to what I think, where I think it will go next. Okay, so to get started, what do we mean by a virtual store? So we need to define two concepts. We need to define a virtual chunk, and then with that, we can define a virtual store. A virtual chunk is a reference or a pointer to existing data living somewhere else. And the reason this is useful is because object storage in the cloud in general makes it rather easy to access data. Like a user can access data from they log into their AWS or whatever, and then they can access data in region or wherever. Like it's much easier than accessing data that's on HPC, for example. But it makes it very hard to change the data that's been written compared to a file system where you can edit parts of files in place. Object storage doesn't let you do that. If you want to edit a part of an object, it's not like a file. You have to overwrite the entire thing. You have to overwrite the entire file object. And that means that there's this like natural incentive to reference data that has already been written somewhere else. So there's this kind of inherent inertia to data on object storage. And so a virtual chunk reference can be thought of as like a pointer to some bytes that already exist somewhere else. And in our case, one thing that you can do that's cool is you can reference bytes that exist inside some other file. So if there's a netcdf file in object storage, for example, then really in the computer's memory, it's like a one-dimensional layout of bytes. But the structure of a netcdf file means that like a particular chunk of, say, temperature data or something occupies a particular range within that file. And so the virtual chunk reference refers to that range. So it's like start and length, offset length. So it says, okay, that range and at this location, because that's the URL of the object and object store. And with these three pieces of information, the URL, the offset, and the length, you can refer to that chunk. So this is what we mean by a virtual chunk reference. And once we have this concept down, we can imagine grouping a bunch of such references together. So a virtual store is simply a data set presented to the user that under the hood consists of many, many such virtual references. And you need somewhere to write down all of these references. We call those chunk manifests. So you imagine like a list of these URL offset length tuples written down into some file. They refer to chunks that are inside some other object, which could be an etcdf file, it could be a grib file, it could be something else. And we say that the whole thing together is the virtual store. The users don't need to know about any of these details. They can just see like a single interface, for example, a bizarre interface, a sort of key value array. They just potentially see this as like one giant array. But under the hood, what we actually have is pointers to specific ranges within other files. And the fact that we can point at ranges within file formats that were never designed with this purpose in mind is very powerful. And so to the user, this looks, in a certain sense of the word, looks like it has the interface of a generic ZAR store. So that's why people say it's a virtual ZAR store. It's still a ZAR store in a sense, but it's got these virtual chunks underneath it. So it's a virtual ZAR store. And because we are only referencing bytes, we have not actually duplicated any of these chunks. So the whole store consists of just the references and like associated metadata, such as telling you that this array is temperature, for example. You don't actually have to duplicate these bytes to create such a store. That's the whole point. And all these files together have then been they've implicitly been grouped together into a single interface. And generally with ZAR, people want to make these like data cube-like objects, and that's the interface they want to present to people. And so you can do this for many files. Millions of files could be all grouped together into a single logical store. Because really it's just many, many little references. Okay, so that's a virtual store. Why is this concept helpful? Like, what problems does this solve? So the first problem it solves, and the most obvious one that people might already be aware of, is that it allows you to cloud optimize data, archival data, without copying or duplicating that data into a new location. And so you take these cloud unfriendly formats that were often designed before like object storage was even invented or mainstream, before S3 became a thing. And it makes the metadata inside those objects more cheaply available. And it also means that when users are trying to fetch data, they're able to do the store is able to do targeted range requests for them and fetch only the chunks that the user actually needs. They don't need to download the entire file if they're not going to use the entire file. And this can often lead to very significant increases in performance of user queries. Together, those two properties are what makes a format cloud optimized. So we would say the virtual store has effectively managed to create a cloud optimized layer over non-cloud optimized archival formats such as HDF. And if you want to read more about how this works, I have a blog post that explains this in much more detail that's intended at an audience of people who are not familiar with this. I'm going to link to various more blog posts in the rest of this talk. And because you're not rewriting the data, then you've effectively achieved a cloud-optimized version without duplicating your storage costs. So if you have a petabyte archive of netcdf files, you can make a virtual store that points at that petabyte without paying for another petabyte of storage, which on its own saves like $100,000 a year or however much it costs to store a petabyte in S3, right? And that's before you get to the query performance part of it. So and I have a nice animation here that we made that shows how the query performance gets faster. Like if you imagine you have a bunch of netcdf files and you wanted to do a query that only needed these chunks, if you downloaded the entire files in a sort of naive way, then it would take you a while because you'd be over downloading what you needed. Whereas if you've already got references to the exact chunks and you only download them, it's much faster. Why isn't this letting me progress? Here we go. Okay, so that's benefit number one. Benefit number two is that it allows the user and the provider to generally abstract over or forget about the details of both individual files and different file formats. So one common problem is that like data archives, data providers have too many files. They have thousands and thousands of individual files, and it's really hard for anyone to navigate. So, and often those files have some structure. So, for example, there may be many small or many like NetCDF files, for example, that if you were knowledgeable about these files, you would know that these form a sort of logical grid. Together they tile over the globe, or they are arranged in increasing time, or there's like a different weather forecast or something like that. But users don't want to have to think about this. They would much prefer, generally, mentally, to interact with a single homogeneous data cube. And if you can provide that to them, it's a quality of life improvement for users, but it's also easier for like AI agents to understand what's in there and so on. The other problem that this can help deal with is the problem of just too many formats. Like users also don't care about the distinction between a HDF file and a GRIB file or whatever. They just want to get like at the data and they want to execute their queries. And so we can use ZAR in this example as a sort of universal interface for various different array format types, because underneath the hood, these are all really just multidimensional arrays. And then once you have the store, you can generally access its contents with just a few lines of code. So this is an example of using ArrayLake, which I'll talk about a bit more in a bit, to access a particular data store, the iMerge dataset. And then after here, you've got a typical Xarray dataset, and you can start to do whatever you want to do with that. The third type of problem that it solves is that you can actually fix some problems or inconsistencies with the archives in the process of the virtualization. So if we go back to our diagram of what's in a virtual store, remember we've got sort of metadata, we've got these manifests with that describe the references to chunk locations. Sometimes the original files might have metadata that isn't actually quite what you want. So here, for example, let's say one of the files has a variable called rainfall, and you would rather it were named precipitation because that's like more CF compliant or something like that, right? Because you're not duplicating the chunks, but you are pulling out all the metadata, you have an opportunity to overwrite that. And so you can correct that metadata in the virtual store without actually changing the original file. You can also do this for individual chunks. So you can have these stores can store both virtual references to virtual chunks, but also like normal ZAR chunks next to them at the same time. So if there's something wrong with the chunks in this particular file, there's nothing stopping you from like logically, not physically, but logically overwriting them. So maybe these ones were corrupted or something and you want to overwrite them, or maybe they were missing. And so you haven't actually edited this file. You've just overwritten the mapping that points to where the chunks are. The final thing you can do is with technologies like IceChunk, which provides this sort of virtual store functionality, then you can safely append new data. And so you can keep adding new files, writing them either as normal chunks or virtual chunks. And when you do that, all you're really doing is like extending the manifests. And you can do this in a way that's safe for operational data, so that as new data arrives, someone else can be reading it even as new data is being written, and there's not like some weird inconsistent state for a second or something. And that's a functionality that just like hasn't really existed within the ZAR array space until now in the cloud. But it's a feature that database people take for granted, like ACID transactions. The final benefit of this whole like virtual store idea is this more sort of like social or institutional benefit, which is that you can kind of sidestep the inertia of existing data systems. So if someone else has a bunch of NetCDF files in their storage and I want to create some virtual references that point at their files, and I don't need their permission to do that. I need to be able to read the files, and I need to be able to let my users read the files. But that I don't need to be able to edit their files, and I don't need them to agree to me doing this. I can just do it. I can just read the data, find the locations, write my own store, which can be in a different location from the original data. which means that you don't have to wait for the data producer to agree to anything. You can just do it. And actually, basically, all of the examples that I'm going to give in the rest of this talk were done that way. Another thing you can do is now that the data delivery, the thing that the users see, is abstracted away from the actual physical location of the data, that gives you a lot more flexibility to change things about the underlying data without changing the experience for the users. And this one's quite subtle, and I'll come back to some examples of why you might want to do this later. But in general, this lowers the barrier for anyone to make an existing archive cloud optimized, because it doesn't have to be the data producer that optimizes it. It could be some like middleman organization. And we see this happening. We have these small, agile, like nonprofits and organizations such as Dynamical, I'm going to talk about a little bit, that are sort of leading the way by there's nothing stopping them from providing the experience they want over these sort of slower moving behemoth organizations that actually produce the original data. Okay, so those are the reasons, a wide variety of reasons why this concept is useful. So how would you actually make such a store? You need a couple of different tools to make a store. You need the first thing that, if you're actually doing this yourself, the first library you'd interact with would be virtualizr, this Python package that I wrote. What this does is, for various different file formats, and it's extensible for different file formats, it looks at the data and works out like where the chunks are, what the byte ranges are, and what the metadata about those chunks is. Like, it finds out that there's a variable called precipitation and that it occupies this range and it has this compression. Then once you have that information about a bunch of different files, it makes it easy to aggregate them all together into one logical cube. You're not actually moving the data, you're just manipulating references to the data. And then it allows you, to write out that metadata and those references into some persistent storage format. So you might pass a bunch of individual netcdf files, join them together. It allows you to join them together using the Xarray API, which is it's like Xarray concat, Xarray merge, etc. It's like something that quite a lot of people are familiar with. This happens to be done in Python here, but there's nothing like inherently Python-centric about this. Like, in theory, you could do the same thing in other languages. Sometimes power users skip this step if they want to. The important thing is that they eventually write these references out into a persistent format on disk that goes in the object storage. Like, you actually write the manifests as files into the object storage, as objects. And the modern technology for doing this is this library, this open source library and format made by Earthmover called IceChunk. So for the purposes of this talk, it's where you store the virtual references. As I mentioned, it allows safe, efficient updates and transactions. So you can think of it as like Git committing to the data. The user interacts with a generic XAR interface. And then the other cool thing that IceChunk does is, when the user is reading the data back, as Amy described, they're reading these chunks, then IceChunk's implemented like in Rust in a very efficient way so that it can maximize throughput. And then finally, you've created this virtual store at a particular URL. There is now like a reference to all of this data, but you probably still want to like catalog that and share it. Earthmover has this other software, this product called ArrayLake, which allows you to catalog and share the data publicly or privately, and it deals with tricky things around like authentication to private data and that kind of thing. But it's really a layer over the data that is actually your IceChunk, your data in your IceChunk stores in your storage. But once you've done that, you can use that as a way to share like this is just a screenshot from the ArrayLake web catalog, where there's various different, each one of these is like a massive data cube, basically these different data sets provided by different organizations. Okay, so that's how you might make the virtual store. Like, let's do a quick tour of different examples of things people have done with this. I realized I forgot to time myself. How much of my time have I used up? Okay, all right. So one case study we did was with NASA. Development Seed also worked on this. And the main takeaway from this one is that you proved that you can pull the data. If you're only pulling the chunks you need, you can pull the data much, much more quickly than a sort of more naive entire file downloading approach. And yeah, you can read more about that one on our website. Thanks to Amy, who worked on that as well. This one was one I did with GOES 16. So I essentially wanted to scale test this idea. I wanted to be like, how big can we do this? What's the biggest like virtual store I can successfully make? And so someone suggested it would be fun to do the GOES 16 archive, which is 300,000 netcdf files, but the netcdf files themselves have tiny chunks in them. So the absolute number of chunks, which is like the metric of difficulty here, is really high, like 7 billion chunks. And I managed to put them in one ice chunk store. And there's a blog post and code about this. And it allows you to do time series access across the entire satellite data archive. So if somebody wants to know how, like, they wanted to look at how reflectivity changed over a particular point on like the Earth's, like, you know, the disk view that the satellite has, they're able to do that by pulling only the chunks they need for that location throughout the entire time series, because now the whole thing has been stacked into a single logical cube. And I did not have to ask or even tell the GOES 16 science team that was doing this. And so you can read about that one there. And this GIF is made from that data I just streamed from the store. You can do this with various different file formats. So those examples were netcdf, but GRIB is also an array format. It's a bit of a weird one. It's notoriously difficult to work with, but it can be done. And so we recently made like format-specific parsers that could understand GRIB and help organize it. And we did that for NOAA National Blend of Models, with a blog post about that. We did it. And then Dynamical, this small organization I meant, they went ahead and did it for NOAA HER archive, which was 14 petabytes uncompressed, 1 billion GRIB messages, 1 billion chunks. And they wrote a blog post about that as well. One caveat here is that because GRIB has its own, like, you need a special codec to decompress the GRIB file, to decompress the contents, but it still works. And yeah, Sean from DevSeed, Matt from Earthmover, and Alden from Dynamical did a lot of that work. You can do it for TIFF files and cloud-optimized GeoTIFF files. They're also array formats. You can use this package called Virtual TIFF, which Max from DevSeed, who's talking later, developed. I did it with Sentinel-1. Here's like an image I made yesterday of like terrain over Svalbard that's pulled from a TIFF from a virtual ice chunk store. You can even do it for the FITS format in astronomy. And I just put this slide in because I wanted to show this really cool picture I made pulling virtual chunks of the pillars of creation in the Hubble Space Telescope archive. And you can also do some other interesting things. For example, you can give one person a virtual store that contains only a subset of the references of the original data. And if you're only working with like open data, you probably might not want to do that. But in the context of our like platform product, we have one customer that wants to sell a subset of their data to another customer. And we're able to achieve this through some like trickery with virtual chunks where we create a manifest that only refers to part of the data. And it's a little bit mind-bending, but there's a blog post explaining how it works. We also do something similar, but instead of filtering in space, we filter in time, which allows us to do like a rolling embargo, where we effectively have like a private version of the data, a public version of the data, and a store that points at both. And we can alter the storage location under the hood in such a way that the user doesn't really need to know that we're doing that. But the end result is that data is like available to the people who are allowed to see it under the embargo, and then becomes unembargoed by our like job that keeps running. So that's a reason why the abstraction of a storage location could be useful. Again, there's a blog post explaining like how that actually works. It's hard to explain the details of that in a couple of bullet points. Okay, so what's the catch? Like obviously there are benefits to this, but there must be downsides. Like this engineering, there's always trade-offs. The main one is that you can refer to chunks, but you can't change the chunks completely. Like any chunk you change, you have to rewrite when you're duplicating it, which means you're paying for the storage again. So if the chunks in the original files were like really, really tiny or like completely not the shape you want them to be for user queries, then you can only refer to them as they exist. If you had like flat map shaped chunks and you wanted long, thin time series chunks, you can't do that and also have your virtual cake and eat it. You have to choose. We're also kind of assuming that the reference files have not been like altered under the hood. And if they are altered, IceChunk has this nice like checksum feature where it will say, okay, this file's been touched since it was committed. Something's gone wrong here. But there is this kind of implicit assumption that like, no, you're not expecting someone to go and like mess with the original file. You're just referring to it as like a static archive. The biggest like way in which this is sort of limited at the moment is that we've got this down and working nicely for like data cube like data, but the ZAR data model doesn't work quite as well for level 2 data, and this is like an area of sort of active, like, development and research. So you could kind of be summarized as like level 2 is quite hard to do today, or it sometimes just doesn't work, whereas level 3 normally works very, very nicely. There's also this problem of like non-trivial security concerns, where because you've got this like arbitrary indirection to arbitrary locations, and the virtual chunks in IceChunk support S3, but also like local file systems. And the S3 bucket could be private. Like the general case of this is actually quite hard to make fully secure. If you only ever work with open data, you don't have to worry about this. But if you do a platform where people might be adversarial or they've got private data, then you have to think about it quite carefully. And there's a blog post about how we solve that as well. I'm going to skip the timeline and this, I think, based on time. Yeah. So I've got like one more slide before conclusion. So all of these features have been built up over time, sort of learning by doing. And we've got to the point where the stack for this multidimensional scientific data starts to look quite modern. Like it's sort of caught up to what the business world have been doing with tabular data for the last 10 years. But then what's happening now? Like what's the new stuff? Obviously, the new thing is AI, right? And one thing that we can do now is we can, because each data set is a special snowflake, then writing a code that translates it to a single virtual store inevitably requires something somewhat custom, right? Like the layout of netcdf files in one archive is different to the layout of netcdf files in another archive. And previously, people have to write this by hand. But AI agents have gotten really good at this, especially if you give them some help. So some of the examples earlier in the slide, I pretty much just did this. I just went to like Claude Code or whatever, and I was like, I want this data set as IceChunk, please. And then it invokes all these tools. It looks online. It reads the documentation, works it out, iterates. And if you give it if you give it the right tools to use, then it can do this really quite well, which reduces a lot of load on the practitioner, the provider. The tool, you can have skills, like dedicated skills. So I wrote this like Claude skill that Rich Signal is going to show how to use later. And MCPs also help. We have an MCP in Array Lake, and together this can work quite well. But obviously, like if you wanted to do this at petabyte scale, you're starting to talk about processing a lot of data, and so generally we're at the point where like this is promising, but it does you probably wouldn't want to just like let OpenClaw go on like multiple petabytes because you might get a big bill, Okay, and what do we need? What do we still need to do to make this better? So we want to make ingestion even easier. So the LLMs help, but maybe we should even try to provide some kind of service to do ingestion as a service. At the massive petabyte scale, you kind of do still have to know some like advanced features within IceChunk and so on. Like for small to medium data sets, you can just kind of do it without learning too much about the internals. But at a very, very large scale, there are some things you have to be aware of, such as manifest splitting. We want to expand what we can virtualize. There are limitations on the things that we can apply this to right now, but we would like to generalize that. And we want to generally, like this problem of, so you create the store, and then you want to give the store to the users, but the users need to be able to discover the store, and they need to be able to get authenticated to the store. And there are various ways that this could be improved. So like Array Lake is one solution to this. We have a free tier for Array Lake coming in the next couple of weeks. One thing that's I find frustrating is that the Earth data login for NASA is like this weird island. And so it would be nice to be able to like integrate those better together. And also a lot of this tooling is a little bit Python centric at the moment. There's nothing inherently Python about it, but it just happens to be that way right now. So it's another way that we could improve access for other communities. Okay, so in conclusion, virtual stores solve many different problems. It's not just like they solve this problem of avoiding duplicating data when you cloud optimize stuff, but you also like have this opportunity to solve various other issues along the way. This technology is like built up as a result of people learning by doing. And the state of the art, in my opinion, is sort of AI and just assisted virtual ingestion into Ice Chunk distributed via Array Lake. Like that's the forefront. Thanks.
One question. We don't really have time, but we're going to allow one question. Yes, Rich, go ahead.
We don't have anybody talking about forecast modeling. That's another benefit of Ice Chunk. You mentioned metadata. You can re-index the.
Will you introduce yourself and start over?
Okay, sorry. Rich Signal, ex-USGS. Another really very cool thing you can do with these virtual things is if you have a forecast model run collection, which is a very common use case, you can re-index like you can change the time dimensions. So, there's a step and a time dimension, aggregate along the once per day, blah, blah, and you get another free like view of your data that you can then use with Rolodex to create best time series on the fly using X-ray advanced indexing. It's like a super powerful, very common use case that virtual data sets solve.
Yeah. The ability to reorganize. You can't change the individual chunks, but you can, in theory, arbitrarily reorganize where they are. And so sometimes you might want to completely restructure how they are laid out to be more intuitive for users expecting a certain layout of where the forecast data sets or something like that. And then you can layer these other tools on top, as Rich is referring to. Yeah.
Okay, thank you so much. Yeah, I mean, Tom, you'll be around for other questions, right, the rest of the week. So thank you, Tom. No, great. That was great. Okay, so this is like our engagement portion. I mean, Tom was riveting, but I want to make sure everybody's awake. So I'm going to have a brief discussion. The question that I've highlighted for this discussion is, how do these ideas address or not the real world messiness of Earth data? So the way that I want to do this is we have these four rows, right? And so Hyliion is like where we're going to sort of Hyliion's where we're going to sort of split these rows. So Hyliion, so if you're on that side of the row, you're a group with that row, right? So Hyliion, Michaela, Dan, you're a group, and then so on and so forth. Same thing on this side, and the people are going to join the rows that they're on. And then the people along this wall are also going to be a group. Okay, so get together with your groups. Okay, 1, 2, 3, 4. Somebody pay attention. Let's see. Michaela's 1, 2, 3, 4. Rich's group is 5, 6. Yeah, Julie, Tony, 7, 8, 9. Okay, cool. Yeah, and then if you have stuff to add to the notes document, please do that as well. You're in group 1. Yes. It's 5 minutes. For the virtual folks, will just be one group on their own. Yes, yeah. Yes.
Hey, Max.
Hey.
Oh, wait. Let me turn my volume on. It's probably very loud in here. Can you hear me?
I can hear you. Actually, the rest of the people
Can I
are
hear Max?
pretty quiet.
Wait. Talk again, Max.
Can you hear me?
Oh yeah, yeah. Sorry, my volume was too low.
Does everyone else in the room hear me too? Or is it
No.
Here?
They're all
Okay,
yapping.
good.
So yeah,
Hey,
you guys
James.
can just
Hey.
talk amongst yourselves. You don't even need a breakout room.
Cool.
Do you want me to pause the recording though, so that I'm not filming you guys in your breakout room discussion?
Sure. It might make it easier for you after two for throwing out their talks.
Yeah. Okay. So yeah, have fun, and
Okay.
we'll just interrupt you when we're back on the mic.
Sounds great. Thank you.
Okay, thanks, Max.
Hey, folks. I don't know if other people are around to chat too. I looks like they might get started.
Okay. But yeah, I'll get back
we
with
should
you
keep
on
talking
that.
about this though. Yeah, for
Yeah,
sure.
yeah, I want to get back with you on it. So I'll send you some things about it. But currently we're kind of right in the middle of it.
Nice.
So it's we don't have a working example of the improved version, and the older version's much slower because of the lack of rechunking of the netCDF data. And one of the things I looked into was materialized ice chunk. And that sped things up as well, where you could, when you created the ice chunk, you could pull out a variable from the netCDF file and rechunk it.
Yeah, usually that's very advisable for any coordinate
Yeah,
arrays or
and
scalar arrays. Yeah.
And that sped it up, and that's what led me to looking into possible these overhead issues, where how to improve things where things that aren't required to select a specific lat long, but can be done beforehand. I guess we're going back.
I don't know why it's in this weird. Do you know how to make it like full screen? I feel like
Screen for this.
I lost,
It's a
or like make it full screen and
Oh,
on
in
the
the
display. Maybe it's fine.
Is there? Yeah. Maybe.
You can do it.
I can handle it.
Yeah.
Okay.
Yeah.
Well, that's a little bigger.
Okay.
You can hide this, I think. What the? Oh, no. That's not what we wanted at all. Okay, there you go. Is that?
A little smaller. Yeah, a little smaller, I guess.
Sorry, I messed you up.
Just one size smaller.
Oh, I see. Fit.
Yeah.
Wait. 100%. Sorry, I messed you up.
It's okay. It's
Or
okay.
is
No,
it-
this
Is the next thing slides?
I can handle it. No worry.
Okay.
No worry.
Wait. You want the slides or you want this PDF?
Amy asked me to put PDF over here,
Oh.
so I have a PDF version.
Okay. Sorry, I messed up your Zoom. Okay, we're almost there.
It's okay as long
Okay.
as I can scroll up and down. Okay, perfect.
That works?
Sure. Thanks. Hey everyone. Okay, this is Hai Liang from JustDisk. Okay, so JustDisk, as mostly people know, it's one of the data center at NASA. So I'm going to be, my presentation is going to be quite higher level compared to what Tom just went through, which is like in great detail, and this make my my presentation much easier, actually. Basically, I'm just going to be using some slides to share our experience based on our most recent effort to migrate certain JustDisk collection to virtual data store in cloud. I'm going to show like what issue we run into and what's the workaround and what's the future plan, things like that. And actually, the work is done by Jack McNeas, who have done most of the development work and me. So
First, background. At Justice, we are required to retire our certain on-prem services based on the requirement from NASA's open data policy and our strategic vision. So one of them is our thread data server, or TDS. As many of you probably know, TDS is a service that is running on a server that is going to be providing data service like aggregation. So basically, if you have many granules that provide the user the capability to do the aggregation by adding them to a single virtual data set. And before we do the deprecation, we want to make sure we have an alternative way to provide the user this capability, basically in cloud, because this is where our data is going to stay in the future. So I'm going to be careful over here. Okay. And we have been doing some research, and apparently virtual data store is a very good option over here. And I don't have to explain more about what is a virtual data store. So, but the key thing here is it's to only store the metadata, not the data itself. And then it can enable the cloud native on-demand access without any data duplication. So, we began to do some experiment based on that. Okay, before doing that, the difference between TDS server and the virtual data store is like for TDS, so the difference between TDS and this virtual data store based solution is TDS. We need a dedicated server to serve the user request to interact with the data and to do the aggregation or whatever service the user is requesting. But for virtual data store, the most of the work is going to be done on client side, and they're going to be interactive with the virtual data store to get the chunk information and to get the original data without downloading the whole thing. So, and at the time we started with this experiment, so at that point, there are multiple solutions like Kerchunk based or like Ice Chunk at that point, which is very early of this year. It appeared Ice Chunk was not that stable yet, and we have very tight deadlines, so we decided to stick with Kerchunk for now. And also, there are different format of choice for this Kerchunk data store, which is JSON or Parquet. And first of all, we tried both of them, and they are both, a variable replacement of the DDS, the aggregation, which is great. And we compare the JSON versus Parquet performance. And our file is actually, like our GPM, half hourly, whatever data set is quite large. And we find Parquet's, it's probably, more compact and also more performant compared to JSON. So we decided to stick with just JSON for now. And also one thing, and I'm going to mention later, is we did find an issue with forward streaming based on this Kerchunk based solution. And I'm going to get this in a moment. The benchmark, we are not the benchmark, basically, the data collection we want to migrate to the cloud is for the virtual data store is based on the popularity of our TDS data collections. We pick up the top 10. And we found this Kerchunk-based solution is going to be work for most of them, except for some GPM data collection with certain issues, and also I'm going to get into detail in a moment. And we did some benchmarking, and we find the generation of this virtual data store scale just mainly depending on the number of granules or files, and also the number of variables. And in the following table, which is over here, we compare the generation time for different collection, which has different number of files and variables. And we basically, this is a list of the runtime for those Kerchunk generation for 1 year of the data set. So and this performance, this metrics was based on a EC2 instance. Sorry, I didn't put the instance type over here, but you got some rough idea like how long they're going to took to generate those Kerchunk files. Then this is a challenge we are running into. Okay, so we found that for the GPMI merge half-hourly granules, they have like some nested HDF5 data groups, which is, which we run into some errors based on the virtualized R solution to parse those collection data, and so basically, virtualized R at that point, the two-Kerchunk method does not support serializing the virtual data tree object to Parquet. And we do have some workaround. For example, like we can use some different parser, like the MRBP parser, to read each individual file and merge them together into some flat and nested groups. And but that it's not scalable, and so we decided to skip this certain GPM collection for now. Okay, so because we have some future plan to use IceChunk. Okay. And also, like what I mentioned, there are some operational challenge, which is, it doesn't support the forward stream very well, because based on some GitHub issue, we are finding that, this Kerchunk-based solution don't support appending very well. So looks like the solution is going to be we have to regenerate this manifest file, like at the whole, so which is not very convenient. So the solution is going to be, looks like it's going to be based on the IceChunk, and as IceChunk is like later, they have a much more stable solution, and due to our timeline and priority, we decided to stick with the Kerchunk for now. So our current production status is like we're just going to be generating the virtual data store for those most popular TDS collection, excluding those GPM based for the historical data only. So and we are grouping them by years up to the year when we generate when we basically make them public. And then, before IceChunk is implemented, we are going to, add each new year one by one. So, and also due to the chunk size, due to, some data collection, we have like so many chunks inside, and we want to basically partition this Parquet file into group them by years, and this is a file structure. We put them in our cloud account, and they're organized by the project, surname and version, and also group them by year. So we haven't published them to CMR yet. So, but we do have the some instruction for the user, basically, which is very important. We want to communicate with the user. Hey, we are deprecating TDS, and this is alternative solution. We do have the Jupyter notebook. We have the notebook on the GitHub page to show people like step by step how to interact with the virtual data store. And this has been written by Chris, which is a big thanks for Chris from our user needs at Justice. And Chris not only been writing the documentation, communicate with user, but also doing lots of testing along with other folks. Yeah, and that's pretty much of it. And really, we are really hoping, in the near future, we can switch to IceChunk. And also, as a matter of fact, as Tom mentioned, we are Amy has a solution for the IceChunk virtual data store generation, and we are thinking about some collaboration, taking some ownership of that in the future, and hope that will make our life easier. Okay, that's it.
Okay, so I'm going to talk about another example of using virtual stores. I'm from NOAA. I'm at NOAA Fisheries, and I'm with our Open Science Initiative at Fisheries. I do a lot of training our staff in using cloud native data, cloud native workflows, and I work with teams who are using the ocean model data I'm going to be talking about, and I've been involved in some of the training for helping teams migrate to using virtual stores. Okay, and I put at the bottom also talking about a variety of other things later. Okay, so NOAA produces a lot of ocean model data. This is one of our core products. It's used for, these are operational models. It's used for navigation, public safety, coastal and ocean management, planning. On the side here, you see some of our main operational forecast. So we have our operational forecast for, navigation, port operations, et cetera. There's a whole lot of them. See all those different ones. Those are all different regions. So, for example, Gulf of Maine, right? Those kind of regions. We also have larger regional coastal forecast, and then we have coastal ocean reanalyses. We have water models, and I'm going to be talking about the one in the middle, which is CEFI. These are regional MOM6 is a type of ocean model used to support fisheries and marine ecosystems. All of these produce massive output, lots and lots of data, enormous amounts of data. Here's an example, just if you haven't seen this kind of data, there's lots and lots of different parameters, but this gives you an example. In the white there, we have, hey, do I have an? Oh, yeah, it works. Okay, great. So this is the data I'll be talking about. This is the CEFI data, and we have different regions. This is showing the Atlantic region. So this example, sea surface temperature. This is some of the data from the other forecast. This happens to be salinity. If you open the slides, I put the link to the slides in the note. You can click on the links. You can explore all these ocean forecasts with the ocean map there. A nice thing, all this data is available openly for free on NOAA Nod in object storage. So great. So we have all that data available. But this massive data creates barriers for use. So many NetCDF files, how to navigate all those files. I mean, here's 820, and this is just a teeny slice. This is one regional model of the CEFI, one hindcast, one region, one grid, one release. And it's just a tiny slice, and it's already 800 files. Each file is, different time period, different, parameter. It really becomes a huge headache for our users to navigate that. So I'm going to be talking about how virtual stores and services built on those stores, that for us, those services are coming from the ArrayLake platform, how those solve user barriers. So I'm going to be talking about this. There are kind of two barriers I'll talk about. One is one you've already heard about, like the barrier that can come if you are serving data versus from a thread server. So typically there will be some limit to the amount of data that you can download. And when you're working with massive files, your users are going to be hitting that all the time. And that's super frustrating to them. And so what we're seeing among our users, they're resorting to downloading all this data locally. Another one is this barrier of navigating so many different files, is complex discovery. Which variables do I use? And like for us, what does that look like? That looks like writing huge documentation to help users understand the file system. And we are putting metadata into the file name because that's how they're scanning to figure out what is that file. They're reading the metadata. Oh, the variable. Oh, what's the time? They're getting metadata from the file names. Okay, if you find yourself writing many, many pages of documentation just so your users can understand your file system and you're resorting to putting metadata in your file names because users are scanning file names, okay, you know you have a problem. It's that's not really where you want to have your metadata. Yeah. So this was the so this is how the virtual stores are helping solve that, and this is our the pipeline we are going towards. In fact, we have a version. I'll provide URLs so you can explore these virtual stores. So we have this kind of pipeline. So this is what NOAA does, right? We do all this science. We create these netcdf files. Doesn't have to be netcdf, but that's what we're creating for the example I'm talking about. And these virtual stores sort of takes all that messiness, all these special snowflakes, and makes it into these standardized things that we have curated for users. So now instead of getting all the metadata by scanning the file names, they load this thing and they see all the variables and they can click on that variable and the metadata is right there. If you've ever used Xarray, you know what I'm talking about. So it's all there, all packaged in this thing. And then this is, for us, what is super, super important is once we have created things, it opens up a universe of tools that are built on this standard format. And I'm going to talk about some of the key tools that are really important for our users. And the reason I want to emphasize that, like once we have created this standard thing, this ecosystem as tool is open to us. Whereas when we had a world of a whole bunch of special snowflakes, we had to always write services for each special snowflake. And that's just not scalable. But if we take this and make this generic thing, now, wow, we can do so much more. All right. So we are not the only group in NOAA that is virtualizing ocean model data. I'm going to be talking about this group that I work with, and that is using ArrayLake. But I just want to make you aware that there is a lot of work that's been going on for a long time about creating virtual stores from all the other data. If you are interested in that work, go to the slides, contact these folks. I put some links where you can read some of the information. Again, all our data is available in object storage. As Tom said, you could also make your own virtual stores if you want of any of this data. Okay, so this is the data I'm talking about. This is the Changing Ecosystems and Fisheries Initiative. These are MOM6 models being run to create variables that are important for fisheries and ocean ecosystems. Okay, here was the old pipeline. We create all those netcdfs. That part's not changing. What we were doing is we had a thread server and then also had the data in object storage, S3, and Google Cloud. And the way the users are getting this is we have this OpenDAP server. And so users were either downloading, they could download from any of these, or they would get data from the OpenDAP server. And they could use that. They have various things like Ferret is a way they might interact with that, or they're using the UI like a graphical interface, or they're doing some kind of programmatic access. Okay, so that worked. Yep, people were using it, but we were seeing problems for our users. As I'll show you, I'm going to show you 3 examples that our users gave to us where they're hitting this bottleneck. Just their code simply doesn't work. They're trying to do something that feels simple to them, and it says, no, I can't do that. And they're hitting these 500 megabyte limits very quickly. So again, they're resorting to this code where they're downloading all the raw data locally, and yeah, not good. And then we're also, as I said, seeing this barrier with they're having a hard time navigating all these files, and we're having to create all this documentation to help them understand all the different parameters and what's the naming. Yeah, okay, hard. Okay, so new pipeline is what I showed you. So we're creating these virtual stores from all the NetCDFs, no more navigating all of that. And I'm going to focus on how, on two services that, or actually I'm really going to focus on one service, and that is OpenDAP service. So, and why that is really important for our users. So once you have this, our users can interact with our stores the way they're always familiar to working with. They use OpenDAP a lot. And it was going to be a deal breaker if we told them, hey, we're going to change to this new way of delivering the data. It's really great. You can do all these amazing things, and you have to change all of your pipelines. You have to rewrite all your code. That was not going to happen, right? They have they're busy people, and yeah, that was going to be a deal breaker. So we partnered with Earthmover to use Array Lake to host the ice chunks. So just note here, if you go to part 2, you're going to learn how to make some ice chunks. It's not that hard. Rich is going to show you how to do that, and you'll put them up on S3 storage. So you can host those anywhere. But for us, it was really important to have all those services, and we're busy doing the science and creating the net CDFs. We don't want to be also managing all these products. So we let Array Lake do that. Is that my timer?
Yes.
Okay, great. So I won't go through, can I go quickly through the examples? Okay, so I'll show you really quickly the examples. So here is probably the simplest example. And this was like where the sigh ran out in the crowd, where they're like, oh, this is fine. Yeah, let's do this. And we showed them this code. So this was something that failed. Super simple. It just gave them a URL, and it didn't work. It's just one variable, and all times one decimal. It's super simple. And they're like, it fails. And with this, all we say is, hey, use this URL. So it's a service built on those virtual stores, and now it works. Not only does it work, it's way, way faster. There's more examples. Here's one example, how much faster it is. This is like 30 times faster. Super important. Okay, so our users are like, yay, great. I don't have to change anything. Now things work, and it's way, way faster. So you can hop on, go into the slides. You can play with that. Poke around, click on this data access. You can see some other cool things, services that it provides, like visualizations. We don't have to program that. If you have questions, go here. All the people you should go and see. Roland, are you here? There's Roland, that guy right there. If you want to talk about Cepheid data, talk to him. If you are questioning about Earthmover, Joe, Tom, over there. Yeah, talk to them. Great. And if you love Hack Weeks and ocean model data, talk to me. Okay. Yep.
Max, are you ready to present?
I am. And I think the original schedule had me at 5 minutes for the lightning round. Should I try to accelerate that a little bit, or how are you feeling about timing?
I mean, you guys can all stay through the break, right? We can be here for another hour and a half if we need to.
All right, I'll try to speed it up. I think people probably want food and coffee or whatever else.
No, thank you for
ESIP
offering.
serves.
Whatever you can do is appreciated.
Okay. I am going to be talking from the perspective of or trying to speak to those who are planning to make virtual stores. And this is kind of a PSA for those people that metadata matters. This might be preaching to the choir at ESIP, but I'm going to do it anyways. I sit at the intersection between software development and standard coordination, which is why I already care about metadata, but I hope by the end of this, everyone in the room will. I think by now, we probably understand what virtual stores are. I'm sorry if you just entered the room. People will probably fill you in during the break, but they provide easier access, faster and cheaper access as well. And when you're using the virtualizr library, people commonly construct the virtual store using X-ray, which provides a function like concat, which concatenates all these different netcdf byte ranges into a single virtual store. This is where the PSA starts. So whatever you pass becomes the truth, not just for one of these files, but for every single file that a user accesses via this virtual store. And in particular, X-Array's default combine attributes method is override. So what this means is that the attribute from the first file that's passed is applied to every single one. And this is an example where that can go poorly. So climate and forecasting metadata conventions include a scale factor and offset, which basically applies a multiplicative and an additive factor to your data when it's read. And if you take the scale factor and offset from the first file and apply it to the entire data store, even if that changes halfway through, your users will get values that are 5 times too large without any warning about what's happening. I think this is not the experience that any of us want when you're using virtual stores. So I think in this case, the solution is kind of clear. For things that actually affect decoding, they should be in codex, not arbitrary metadata. But there are a lot of cases where this requires kind of nuanced decision, how you want to concatenate and merge not only your data, but also your metadata for these millions to billions of files. And that's the PSA part. The kind of call to action is to get involved. I think we as developers don't want to be making these decisions unilaterally. What I'd like to hear is your opinion about whether virtualizr should be more opinionated. Should we refuse to merge decoding attributes that conflict, or make people provide arguments and not provide defaults? Or should this remain with the store creators and we just share PSAs that you should know your data sets and your users and how you want to construct the store based on the inputs? And I have linked here a GitHub issue, which is one entry point where you can share thoughts. But more sustainably, I think what we need is a community around these types of practices. Amy started this with the virtual stores co-working session. I don't mean this PSA as a kind of dissuasion from creating virtual stores. We've seen how important they are, how it really is the only way to access data in some cases. For example, Eli's example, where you just couldn't load the data and then you could load it in a matter of minutes. We just have to do this carefully. So I encourage you to join the Zulip, which is open to everyone, and also reach out to Amy about the virtual stores co-working. And I hope I've convinced some of you that metadata really does matter in these cases. That's all I have for today.
So after looking at the usefulness of virtual data stores, one of the things that I'm going to talk about is how can we empower users and producers to be able to use this technology in a faster, more efficient way. And one of the things that we're doing with this work at the Earth Access is precisely that. So I'm going to present just what we have been working lately on that front. If you know Earth Access, you know that it's...
sorry to interrupt. We can't see the slides on there.
No? Oops.
Sorry for cutting off your flow.
No, thank you. Thank you. Okay. Good? Yes.
Great. Thank you.
Okay. So if you are familiar or not with Earth Access, it's a library to access NASA datasets that are behind EDL. That's the main function. So this is the 3 lines of code that you might recognize, which is you log in into NASA, search for data, and you get your data. Now you see something different here, which is a function called virtualize. That function, it's a wrapper around virtualizer and all the technology that Tom presented at the beginning. It's really simple. It takes care of all the authentication and all the virtualization. You can pass all the keyword arguments. Okay. So once that we authenticated with our data login, one of the issues when we're dealing with virtualization is that you have to have in the case of NASA data, you have to have the permissions to get the netcdf files, and you have to have the permissions to read them once that you get the virtual chunk references. So Earth Access takes care of that. It's just you log in once and forget about it. Then one of the other cool things I think somebody mentioned here about like these partial views that you can have in virtual data stores, because CMR is a very powerful search interface. You can imagine a data set that is like, say, daily, and it's about like, temperatures in the different parts of the ocean, right? So you can search for your use case. And if you're doing some research and say like extreme weather events in the Mediterranean, you can search for that or particular subset of granules and create a virtual store out of them. So you start with a search that can be like, as broad or as particular as you want it, get the results back from CMR. And those results are the ones that are going to be virtualized with early access. So that will allow you or allow users to like have like, seasonal data sets, for example. You don't have to filter post-process, and say like, give me all the summer granules. You can do it beforehand. So that is the thin wrapper on virtualizers, open virtual MF datasets. I think virtualize sounds better too. And we have some tricks under the hood. Like one of the cool tricks here is that NASA already parsed some of those data sets. So we have some of that metadata in the form of another format called DMRPP. And users don't have to like go and parse the binary files. So it is basically a metadata translation tool that speeds up the creation of virtual stores by an order of magnitude. And it allows users to do this on the fly if they want to. So they don't have to necessarily serialize that into like, say, Kerchunk or IceChunk. You can do it in memory. This is how it works. This is a slide from James here. I didn't ask you for permission, but but I quote you. So this is what early access does by default. Goes to CMR, gets the granular metadata information, and say, hey, you have DMRPP files, so I'm going to use virtualizer and this parser to translate that metadata. That's really fast, almost instantaneous. It translates into SAR metadata. So then you have like a virtual data cube of your data, which represents as an X-array. And that's really cool. So I don't have the metrics here, but like you can, all of the metrics, but you can imagine like, not just from the all the cool things that we've seen about virtual store, but just from like the user experience from users saying like, oh, this used to take forever because you have to download the granules to do a sneak peek. Now you can virtualize the collection or a few granules if you want, like 10 granules, create the virtual store on the fly, and get your data in a matter of seconds in X-array. But it's a good thing that Hailiang also presented something that it's like not so much for users, but for data producers. And early access wants to help here too. So that is like, oh, I have a collection, but it gets, keeps being updated every month with n number of files. So virtualizing in the first sense is like, okay, I have granules, I'm going to virtualize, and you can serialize them into IceChunk or Kerchunk. But how do you keep that virtual store up to date? And it gets complicated because Parquet is not appendable friendly. Yes. And most of the virtual stores here that NASA uses are Kerchunk, not IceChunk yet. But you don't have to regenerate the reference from scratch. You already did that work, and it shouldn't be lost. So even though you have to rewrite the Parquet file, you can like open those references as a virtual store and say, here are my 10 virtual chunks, append to that, and then save that Parquet back. So yes, you're replacing that Parquet, but you're not starting from zero. And the overhead is like very little. I think I explained this slide. And you see the code is not is not pages of code. It's really simple with the X-array syntax. It's just concatenate the old one in the new one. But you have to open it as a virtual lazy store. You see that load equals false. That says don't materialize this manifests. So it will open that Parquet file without materializing anything. Oh,
Sorry.
yeah. And the things that we're working on now, it's like the same thing with IceChunk, which is work in progress. But once that we get that, we have this like, two sides of the same coin in the same library, which is virtualizing data and using that virtualized data in a very, user-friendly manner. Yeah, this is for later. But one last thing, why we do this for things like this. Thank you.
Okay, thank you.
Well, hello, I'm James Gallagher, and I'm from OpenDAP. Thank you, Eli, and also from EED3, a contractor. And I'm going to talk about chunk manifests and a standardization effort that Miguel Jimenez, who's also from OpenDAP, and myself and Amy kind of started working on in the last couple of months. And I guess the question, and so this was actually a much longer presentation, so I'm gonna turn it into a fast talk. So I'm going to skip over the background on chunk manifests because I think we've talked about that quite a bit. And also I talked about some of the history of HDF 4 and 5, which is sort of how we got to this place. But here's just a quick overview of what I see going on in chunk manifests. And I think this is useful to look at to understand why we might be interested in, at this time, starting to develop a standard that would allow chunk manifest implementations to unify on some common concepts. And the action really happens all the way on the right in the client. And what we're really doing, and several of the presenters here today have talked about this already, is we're taking operations that used to be close to the data, and we're now moving them to the client. And the way we're moving them to the client is by taking certain information about the internal structure of our data stores and re-representing that as data itself. A chunk manifest, we talk about it as metadata, but it's really data. Okay, and there's a funny duality about data and metadata. We'll go back to that in a minute. But we're moving those data into the client, and then we're saying, okay, client, do your work here. The problem is that the work is often very complicated. So we've talked a lot about the common elements in a chunk manifest, the size, the offset, yada, yada, yada. Okay, so we're not going to go over that again. But the thing is that the clients, when they get the manifest, it mostly is what they need, but not quite, because it turns out that data are stored in many different ways. Tom used the great phrase snowflake, or that's a word, I guess. But anyways, it depends, I suppose. And so, every data set is in some way unique. And the thing is that in order to use a sort of a generic chunk manifest in an efficient way, clients oftentimes have to do really complicated software operations, like taking the chunks that are spread across some area in an actual file and amalgamating them, bringing them together and transporting them as a single unit, but recognizing that that single unit is actually a whole bunch of separate units that now have to be treated separately by the client. And this is the same kind of thing that device driver developers had to do with spinning disks a long time ago. So it's a solved problem and it's understood, but it's also very complicated. So the question is, can we, through standardization, simplify the work of these client developers, who will only grow in number? There's already 3 or 4 of them, right? But this is going to be something that hundreds of people probably have to do. So is there enough information now to start developing a standard? And what are some issues that we might have to deal with in such a standard? And so just super briefly, I didn't even bring a timer for myself, so I don't know how far over I am, but we have the basic chunk concept, but then we have these other outliers like inline data. Also, a lot of these systems, IceChunk, DMR++, they take things that don't fit well in that chunk model, and then they just encode them as data and put them into the metadata file, into the chunk manifest. So that is a hard thing for the clients to deal with. And we have other things like external data. In order to represent information in a format like HDF-EOS as an API computed values and made them look like they were part of the file, but they never were. And those things can be extremely large with level 2 data, which we've already heard about from several people, is difficult to work with chunk manifest, but there's a lot of it. And so how do you work with these computed things? And so what you do is you pre-compute them and you store them in files. But now the thing that thinks it's representing information in one place is actually representing things in several places. So these become sort of primitive virtual data stores. And this kind of goes on and on. So there's some implementation challenges here, but the key thing to understand is that the chunk manifest holds the information that's used to read data values, and these clients, efficient client access can complicate writing clients. It sends people back to effectively writing these little device drivers. And there may be ways that we can modify how we build and store the chunk manifests to guide those client developers to do things more efficiently and make it so that people have to reinvent these systems more and more, or less and less, rather. And the thing I heard just in this room was, oh, IceChunk is developing the superchunk algorithm, which is this chunk amalgamation thing. And it's like, why are we doing this over and over again at this point? I mean, a lot of us are old enough to have been through this process before with other technologies. So that's my pitch.
Thank you so much. Yes.
Thanks very much for staying 5 minutes late.
Yeah. Okay. Thank you all for staying. We do have a 20-minute break, and then you can come back here. We're going to have the agentic coding workshop with Rich and Tom, and then we're also going to have 1 or 2 discussions, continuing on with the discussion with James Gallagher about chunk manifest specifications, as well as talking about virtual stores in enterprise data systems is going to be my discussion topic. If you're interested in the workshop, I think you're supposed to go to Tom and give your email for access to Array Lake. So thank you.